Welcome. In this video I'm going to show you how you can perform a Freeman-Tukey Goodness-of-Fit test using Microsoft Excel. I'm not going to explain if you should be using this test. This video is more about how to actually perform the test, not even on how to read the output. There are some who, at least the modified version, think it's even redundant compared, for example, to a Pearson chi-square test of goodness of fit or a g-test goodness of fit. Anyway, you're here, so let's dive in. I have some data in column A of different marital categories, and the first thing I need is the number of categories, which in this case is actually 5. Then I need to actually get the observed count for each category, so these are the 5 categories. The observed count can be simply done with a COUNTIF function and then copy paste it down. And for the expected count, if you don't have any, I probably want to expect that each of these was chosen equally often, so I'll simply divide the total sample size divided by the number of categories. And the total sample size is of course simply the sum of these. Then we need to subtract the square root from this one and this one from each other, which you can see here, and then square that result. So we can simply use the square root function twice and then use this radical sign, I think it's called a radical sign, and a 2, and that should give you those results. We then determine the chi-square value, because this follows a chi-square distribution, which is then simply the sum of these and then multiplied by 4. So that's what's done here. We also need the degrees of freedom, which is the number of categories minus 1. So that's our original number of categories minus 1, which is in this case, of course, 5 minus 1 equals 4. For the significance, we can then use the chi-square distribution function, or we can use the new chi-square dot dist function and then set cumulative to true and then subtract the result from 1. We can also use the new RT function, the right tail, and then we don't have to do the 1 minus. Or we can even just say I want to perform a chi-square test, and then you feed it you should feed it all, of course, the observed counts and the expected counts, and then it should give you the same result. Now in this case it's so low that it's all rounded to 0. Usually we would reject the null hypothesis if this is below 0.05, that's the usual threshold. So in this case it's far below that, so in the population most likely these are indeed not chosen equally often. There is a modified version of this test which uses, as you can see, a slightly different formula. So that means that instead of doing the square root of 1 minus the square root of the expected, we do the square root of the observed count plus the square root of the observed counts plus 1 minus the square root of 4 times the expected counts plus 1, and then square those results. Then copy paste that down, and then the rest goes the same way as in the previous one. You could apply some corrections. There is a Williams correction which uses this fancy formula over here. We have all we need for this. K is the number of categories, N is the total sample size, and again those degrees of freedom. So just plug all of those values in and then divide the chi-square value we originally had by this correction. So then we get, in this case, 1165.89 instead of the earlier found 1166.5. So it's not a big difference, but it's a small difference in this case. There's also a ES Pearson correction. So what that does is simply multiply the original chi-square value with the sample size minus 1 divided by the sample size. Last but not least, there is a Yates continuity correction, which should actually only be applied if you only have 2 categories. But just to show how it works, what you do is you adjust the frequencies and you adjust them such that if the observed count minus a half is greater or equal to the You subtract a half if the observed count is greater or equal to the expected count, and you add a half if it's the other way around. So that's what's being done in here, and then you actually repeat all the steps from before. You write down the expected counts, which of course didn't change, and then simply take the square root of each, or use the modified version. Sum them all up, and you have your new chi-square value. There's an alternative version for this Yates, because this might sometimes get negative results. So what you could do is subtract a half first if the expected count, and then if the expected count is greater, you subtract indeed a half. The other way around, if it's less than, then if you add a half and it's less than the expected count, then indeed you add a half, and otherwise you just keep the original expected count. So that's what's being done here. The expected counts didn't change, and this formula is the same as the one over there. Again, sum all the results, multiply by 4, and you have your adjusted chi-square value. Right, and that's how you can get the output that you probably were looking for. In a separate video, I'll show you how you can do this with my stikpet E function, but for that you need to install my add-in. Alright, I hope this was helpful, and thank you for watching.